Hello, I'm Francesco Sarandrea, and I'm going to present the Virgo GlitchFlow digital twin demo. The Virgo interferometer is a gravitational wave detector that aims at studying gravitational waves coming from outer space. And the digital twin that we're working on aims at improving the detection rate by identifying and generating, using generative neural networks, glitches, which are transient noise artifacts that can pollute the data and prevent the detection of gravitational waves. So in the scheme that we see here, we see that our aim is to take the data from safe control channels. This is the data that is detected by auxiliary and sensors, which are present in the interferometer, and they are blind to the gravitational wave, so they are blind to the astrophysical signal. And so we take this data and we want to feed it to a generative neural network that should be able to map the glitches, so these transient noise artifacts that happen exactly at the frequency range of gravitational waves, takes the glitches and then is able to map them into the observational strain channel. If this is achieved, then we be able to, first of all, do some vetoing on portions of the data, because we'll be able to tell that some strain data is corrupted by the presence of glitches, and so we could skip the analysis. Or, as a further step, and a more sophisticated one, if we're able to generate the glitch faithfully, then we could perform denoising, which consists in subtracting the generated strain data from the real strain data. If we've been able to generate the glitch correctly, this would result in a cleaned strain observational data channel, which would be free from glitches and only contain the astrophysical signal. Here we see a cartoon, just a little scheme of the actual digital twin, so with the different modules. So we can see that the data coming from Virgo, this is data that is stored at INFN, would be transferred to Analyses, which is a module that performs the channel correlation check. So the auxiliary channels are present in a vast number. So we're talking of the order of tens of thousands or hundreds of thousands in some cases. And so what is necessary is to find which channels correlate with the observation strain channel in the presence of a glitch. So what Analyses does is gives the correlation of each channel with the strain channel in the event of a glitch. And so these allow us to restrict the number of channels that are studied and to just only select the ones that strongly correlate with the strain. Once this analysis has been performed, the data is then fed into preprocess API, which is a module that performs some preprocessing, which consists in some standard cleaning techniques such as whitening and bandpass filtering, as well as cutting the time frames, which we're studying, into smaller sections, which are more suitable for the training and then inference part in the neural networks. Then, if we are performing the training, this preprocessed data is moved into the GlitchFlow, which is the actual module that contains the neural network. And so we perform the training of this network. Once the training is performed, the model is stored into a model catalog, as we see. And this allows us then to go into the inference part, which is the bottommost part of this graph. So we see that during inference, the same preprocess API module is used, but then the data is fed into generative API, which also calls the model from the model catalog. And then so we were able to perform inference and then generate the glitch as we expect it to be seen in the strain channel from the auxiliary channels. This slide concerns the data transfer that we will see during the demo. So we see here that there is the glitches or are contained within some 100 seconds files, which are in this GWF format, which is the standard format for gravitational waves. The little cartoon of the lines shows how sometimes in the data acquisition, it is necessary to download more than one file per glitch. And this is because what we want to have are files of 6 seconds, which are centered at the time of the glitch. So this means that the number of files that have to be downloaded can be as high as twice as many the number of glitches that we're interested for the training and the inference of our model. At the bottom of the slide, we see again a scheme that shows the data flow and the data lake that is at our disposal. So the data is the raw data, so the GW files are downloaded into a local storage. Then from this local storage, we're able to access the data lake, which is created using Rusho. And we see that the data lake contains two storage elements, an NFN Rusho storage element and a Vega Rusho storage element. So from local storage, there is some pre-processing performed. Essentially, the number of the channels are selected, and the length of time of each file is reduced. So we only keep 6 seconds per file. Then this file is uploaded into the INFN storage element. From INFN, we're then able to transfer it to the Vega storage element. And this is done using Rusho rules. Now, thanks to Interlink, which is another piece of software that has been developed by Work Package 6 in interTwin, thanks to Interlink, we're able then to access a Jupyter Lab environment directly at Vega. And so because the file has been transferred into the storage element, we can then access it directly in the Vega file system using this Jupyter Lab interface. And this is what we will see in the second part of the demo, where we do perform the training and inference of GlitchFlow directly in Jupyter Lab present at Vega. And we see that in the Vega file system, we're right before the training started, we're able to do the second part of the preprocessing, which essentially consists in creating these 6-segment files and converting them into a more suitable format, which is H5PI, which is better for ends than the GWF. Then as a last slide, we see just a short representation of the performance of the model, which for vetoing is very good. So we see we're able to perform vetoing with a high level of accuracy in almost all cases, with the exception of when the SNR, which is the signal to noise ratio, is low. Now, of course, if the signal to noise ratio is low, it means that the signal, the astrophysical signal, or the glitch is hidden by some background noise, which makes it hard to detect. So we expect the accuracy to be lower for a lower SNR. So we distinguish between generation accuracy and position accuracy. Generation accuracy essentially measures how good we are at identifying a glitch, so being able to tell if a glitch is present in the strain, if we see it in the auxiliary channels, and we see it's very high. And then the position accuracy refers to the position in the frequency time space. So if you see at the bottom of this slide, we see that these glitches are represented by these 2D images, which are spectrograms. And on the y-axis, we have frequency, and then the x-axis, we have time. So we see that the glitch is these yellow signals, where the brightness of the yellow indicates the intensity. And the position in these 2D images tells us the frequency range and the time range of such a glitch. And so it's important not only to being able to say that the glitch is there, but also to identify where it is, so at which frequency it occurs and at which time. And we see that, again, the accuracy is very high if the SNR is high enough. So we're now able to go and show the actual demo. So as we said, the first part concerns the data transfer, and we'll be able to see how we can, just using the terminal, use Rusho commands to perform it. So we perform a WMI, which tells us information about our account, and then we can check that indeed we have the NFN and Vega storage elements. Now the script that we launched is downloading the files from the NFN, and it's downloading them locally, then selecting the channels, and subsequently is uploading them into the data lake, so by uploading them into the NFN storage element. So this is a time lapse of the files being downloaded and uploaded. And as soon as this is done, we'll be able to check that the files have actually been downloaded into the right place. So we can list the data set, which we call SL glitches, which contains all the files that we see here. And then we can check where the files actually are. So we check the address of these files, and sure enough, we'll see that the address is in INFN storm, which means they are in the data lake. Each file has some timestamps indicating the time of the glitch. Then we use a Rusho rule to transfer the files from the NFN to Vega. And we see that it's very quick. And then using Rusho, we can check the rule info and indeed check that the files are being moved into Vega. And so we can see here then, once this is done, that the data set is indeed in the Vega Rusho storage element. Then we can move into the file system of Vega and verify that the files are there. The second part concerns a digital twin, so we will be using Jupyter Lab environment on Vega directly. So we want to perform some further preprocessing of the data. So what we do is we check where the data is, we find it in the file system, and then we can use this generate H5s to indeed convert the data into a more suitable format. So here we're importing some packages, and we can very easily, this is a very short Python script, convert the GWF files into HF files, which would be then used for the training of the neural network. So we see here again a time lapse of this happening, and then we can check into the folder that we created that the files are there indeed, and they are in the right format. Now we can do use the preprocess API, which is the one we showed in the second slide of the presentation. And we see here that what we can do is construct a data frame, which is suitable for ends in the preprocessing. And then what the preprocessing is essentially doing is identifying a suitable interval, both in time and in frequency, so that we can isolate the glitches and more easily use them to train the network. So this is what is being done and is performed this Q transform data set. A Q transform is the type of spectrogram that we're using during our analysis. And what you see here is that it's creating a 64 by 64 images that then will be used as the single files used during the training and inference. And once this is done, we're able to launch GlitchFlow. So GlitchFlow is in here, what we're doing here is loading the data that we previously created, and we see here some examples of the glitches as they appear. Then we split the data into training and tests, which is as is customary. Then we normalize the data. We find that normalizing the data improves the convergence and performance of the network. And then we define the ResNet. The ResNet is the neural network that we're using to perform this generation. Is a ResNet with tens of thousands of parameters. So it's a pretty complex neural network. So we see the pre-trained generation is just a blank image, and we compare that to the actual data, which clearly shows the presence of a glitch, which is high intensity. And then we do the actual training. So we do 15 epochs. We have a very fast overfitting, but we only use the model before the overfitting. So we save the model before the overfitting, and then we can perform the inference. And we see here that inference is working well, because it will show the real generated and then the subtraction of the two, together with the glitch as observed in auxiliary channels. And so we can see that the model is working as expected. Thank you very much for your attention.